Okay, by popular demand, we're going to have a look at the solution to exercise 7y question 4, which is the cylinder in the cone. Just to set the scene here, we've got a cone. We're told the cone has a 10 centimeter height, so that 10 centimeters goes all the way up. And we need to be really careful here about what's what. We've got a cylinder inside. It's got a radius r, which is just that little distance across there, really important. And this distance across here, so the distance for the radius of the cone is 6. The radius of the cylinder is r. The height of the cone is 10. The height of the cylinder is h. Right, our first task is to find an expression. All right, this is sometimes easier to go cut right to the chase. We want to maximize volume here. So maximum volume of the cylinder. So obviously what we can do here is we can stick a cylinder in that just sort of squeezes in here, but we could go for a really low sort of squat cylinder down here, couldn't we? All right, so it's got quite a big radius, but a really short height. Or we could go for a really tall cylinder, really high, but really tiny radius. What's going to give us the maximum volume? This is a huge question, because we want to get a cylinder in this cone, but we want it to be fit. We want to be able to fit as much stuff in there as we can. So this is keeping us awake at night. This problem, we have to solve it. So so that's where we're heading. We're heading for a volume. So perhaps we should whack that down as our aim, because I think with these sort of questions, with optimization questions, get your aim down. It gives you a real focus. So aim is to maximize volume of the cylinder. Maximize the volume of the cylinder. Right. So first thing we're going to do is what we need to do is get an expression for the volume of the cylinder. But before we do that, let's do what we're told. Part A, find expression for r, the radius of the cylinder, in terms of h, the height of the cylinder. Now this is really what I wanted to do this for, because there's a little technique here that you won't know about until you've been shown it. But next time you see a cylinder in a radius, cylinder in a cone, which, let's face it, could be any time, you're going to know how to go about solving it. So what we need to take out of this, I'll show you. I'm just tracing the outline here. Is these overlapping triangles here, overlapping similar triangles. You'll have seen these when you did similar triangles way back when. So there's the big one and there's the small one there. So if we just pull that out now, so I'll just reproduce those triangles. Okay, there it is there. Now that height there, that's the whole height. So we're going to cut across here that's that line there. So this is my r. That's that distance there. This is 6 down here. Now you can see where this is heading, can't you? That's h there, just from there to there. And the whole thing is, and we need to know the whole thing, the whole height from there to there is 10. Okay, that's from there to there. So using similar triangles now, the similar triangles aspect of this is that we've got equal angles there, and we've got a common angle here. So we can say, therefore, that these triangles are similar, and therefore r over 6, small to large, is equal to small is this here, not h, but this here. This is 10 minus r. They give us a little clue, or 10 minus h, sorry. They give us a little clue here, you can see, just in the diagram. They give us that this is 10 minus h. So 10 minus h in there. They don't have to give us that. We have to be clever enough to work that out ourselves. So r over 6 equals 10 minus h. If you can see what's going on, 10 minus h over 10, which is the corresponding side. See, small side, 10 minus h, large side on the large triangle, 10. So this to this equals this to this. Beautiful. Now we need to write r in terms of h. That's what we're asked to do. Expression for r in terms of h. So we just multiply across and we get 60 minus 6h over 10. Okay, that's looking pretty good. So that's my r. Now let's find expression for the volume of the cylinder in terms of h. Okay, the volume of the cylinder. We're getting closer to what we're trying to achieve here. So the volume of the cylinder, maximize volume. So the volume of the cylinder is pi r squared h. That's what we got. We got r is my radius, h is my height. That's my volume. Obviously, I can't be dealing with two variables. I've got r in terms of h here, so that's great. So I'm going to change this to pi. I'm going to square this. It's going to get messy. 60 minus 6h over 10. That's all squared. Pi r squared times h itself. I'm going to pause and do a little bit of algebra. Okay, I've moved this on along a little bit. So going back up here, we've got the volume is pi r squared h. So I've subbed in my r, which is, I've simplified back a little bit, divided through by 2, so I've got 30 minus, would have been smarter down here to say that was 30 minus 3h over 5. So I've made that adjustment in there. I've squared that fraction, so that's 900 minus 180h plus 9h squared over 25. Remember that h is out there. Then I run that h through, so that's just pi times this. So I pull out 9 as a common factor here, so it's 9 pi over 25 by that lot there. Now dVdh, it's nice to hold this constant outside and then just deal with what's inside. So it's 100 minus 40h plus 3h squared. And the second derivative, which we're asked for, again, we can just hold 9 pi over 25 out and derive what's inside the brackets, minus 40 plus 6h. Perfect. They're going to be really useful for us. To find the maximum, firstly, we make dVdh equal to 0, so I'll make this equal to 0. Divide both sides by 9 pi over 25, so that's gone. So really what I'm solving here is, as you can see, 3h squared minus 40h, which is this quadratic here, plus 100 equals 0. Alright, now I'm looking for two numbers here that multiply to 300 and add to minus 40. I reckon that's minus 30 and minus 10. Do that job for me, so I can write this as 3h squared minus 30h minus 10h plus 100, which goes 3h, h minus 10 minus 10h minus 10 is equal to 0, so therefore 3h minus 10, h minus 10 is equal to 0. Just tidy that up a bit. H minus 10, so therefore my solutions are h is equal to 10 thirds or 10. Now is 10 a sensible height? 10's the entire, if I choose h equals 10, I'm not gonna, that doesn't seem to make sense to me. If I make h equal to 10, I don't see that's possible, so h has to be less than 10, so this is my solution here. So I've got h equals 10 thirds. Now I put that back in. Actually, firstly what I do is verify it's a maximum. So I put 10 thirds in here. So the second derivative equals, so the second derivative is equal to 9 pi over 25 times minus 40 plus 60 over 3, which is 20. So that is minus 20, so that's negative, that's less than 0. So therefore we got a max at h equals 10 over 3. And then when h equals at 10 over 3, we put h equals 10 over 3 in here. We get 10 for that. 30 minus 10 is 20 over 5 is 4. R is equal to 4. So we get a max when h is 10 thirds. When h is 10 thirds, just 3 1/3, and when r is equal to 4. So we've solved the problem, and hopefully that's been of some use to you. Okay, cheers.